Most people know that the planets and other objects in the solar system move in a constant orbit around the Sun. But why do the planets revolve around the Sun? And how are they stable in their orbits? Two forces are responsible for keeping the planets in their orbits. Gravity is the primary force that controls the orbit of the planets. Gravity is the mutual attraction between two mass objects in the universe. Any two objects in the universe with some mass attracts each other. The attraction decreases with increase in distance between the objects. Sir Isaac Newton discovered the force of attraction and introduced it as Newton's law of gravity in 1680. Through gravitational force, each object in our universe attracts other objects towards itself. Gravitation is the study of the interaction of two masses. The heavier of the two masses is referred to as the source mass, while the lighter is referred to as the test mass. Before 300 years, we do not have the knowledge about gravity. Ancient philosophers thought that the planets and stars were part of the gods' realm and followed a natural motion. They did not realize that gravity is involved. The most predominant theory of the structure of the universe in the ancient world was the geocentric model. It says that the Earth is at the center of the universe, and every other celestial body rotates around the Earth. Greeks were strong supporters of this theory. In early 1500s, astronomers like Galileo and Brahe discovered that Earth and other planets revolved around the Sun. This is termed as heliocentric model. Later Kepler showed that they moved in an elliptical orbit, not a circle. In the later years, Newton found that any object at rest remains at rest, and any object in motion remains in motion at constant speed and in a straight line unless acted on by an unbalanced force. This is the Newton's first law of motion. Also, he realized that some force must be acting on falling objects, because otherwise they would not start moving from rest. Newton also realized that the moon would fly off away from Earth in a straight line tangent to its orbit if some force was not causing it to fall toward the Earth. Newton called this force as gravity, and determined that gravitational forces exist between all objects. The work of Galileo, Brahe, Kepler, and Newton proved once and for all that the Earth wasn't the center of the solar system. The Earth, along with all other planets, orbit around the Sun. Astronomers, J.C. Adams and U.J.J. Leverrier, later used the concept of gravity to discover the planet Neptune. They realized that there must be another planet exerting a gravitational force on Uranus because it has odd deviations in its orbit. Newton's law of gravity and Kepler's law governs the planetary motion. According to Newton's law of gravitation, every particle in the universe attracts every other particle with a force whose magnitude is directly proportional to the product of their masses. Thus, increase in mass of any object increases the force. For instance, if a mass is doubled, the attractive force also gets doubled. Also, this force is inversely proportional to the square of distance between them. Thus, if the distance is increased between masses, the attractive force decreases. If the distance is increased by a factor of 2, then the force of gravity decreases by 4 times. Thus, Newton's law of gravity can be written as displayed. If we substitute the mass and radius of Earth in this equation, we get the value of acceleration due to gravity. In the early 1600s, Johannes Kepler described 3 laws of planetary motion. Kepler was able to condense his mentor Tycho Brahe's carefully collected data with 3 statements. Using this law, we were able to define the motion of planets in a sun-centered solar system. Kepler's laws are still recognized as an accurate description of the motion of any planet and any satellite. Among 3, only law of ellipses will be discussed here. Law of ellipses explains that planets orbiting the Sun in a path described as an ellipse, and the Sun is located at one of foci of the ellipse. Isaac Newton's cannonball theory is really a pretty good analogy to understand about the orbit. Consider a high mountain on the surface of the Earth. When a cannonball is fired from this high mountain, the cannonball follows the parabolic arc. If we increase the speed of the ball by adding more gunpowder to cannonball, the ball fall will further apart. At very high speeds, the ball may have chance to have an orbit around the Earth. This orbiting of the ball is the nothing but the fall of the ball. This is basically how a spacecraft achieves orbit. It receives initial rocket thrust and orbits for the rest of its life. Modern spacecraft are more efficient, and they include rocket engines that allow for periodic orbital adjustments. Rockets need a speed of about 30,000 km/h to achieve the orbiting. After that, spacecraft will continue orbiting around the Earth. No more propulsion is necessary, except for occasional minor adjustments. If there was only gravity, all planets would fall into the Sun by traveling in a straight line. So there must be some secondary force which makes Earth and other planets to be in orbit at certain distance. The second force is the inertial force.